In this video, I will show you how we can start from the expression that I found for the magnetic field created by a current carrying straight wire, and how we can simplify this if we make some one particular approximation. So I found if this is a straight wire and there is a current I, if we are here and this is the midpoint of the wire, then actually what I found is that it's the magnitude. Okay, the magnitude of B is given by this expression. You can always find the direction of the magnetic field using the right hand rule. Now, I really made no assumptions when I derived this expression. I just said it is a straight wire and has a length L and current I. Now, there are cases, and it does happen actually fairly frequently, fairly often, that the observation location where we want to find the magnetic field is fairly close to the wire itself. Now, you have to keep in mind when we say large, small, close, far, far away, it is always these expressions need to be quantified. You have to have a way of making it specific. What do I mean when I say that the observation location is fairly close to the wire? So if you do get very close to the wire, then the length of the wire, so this length, this will appear to be much greater than the distance. Okay, let's say if you're here, if this is where your observation location is, then the length of the wire will appear to be much greater than the distance from the midpoint of the rod. So if I make the assumption that x is much less than the length of the rod, then I'm gonna see how I can simplify that. The magnitude of B, the constant remains. Of course, I still have the current I, and then I have L over X. Now this is what I'm gonna do. I see in the square root I have x squared plus L over 2 and this squared. Now, when x is much less than L, this term x squared will be significantly less than L squared over 4. If this is a very small term compared to this one, then what I will do, I'm gonna start with this square root and say, well, in that case, this is approximately equal to the square root of L over 2 squared. And of course, you can cancel out the square root with the square, and you got L over 2. So what I have here is simply L over 2. Now, let's make this approximately equal. Okay, if x is much less than L. And then this is mu naught over 4 pi. Now the L with the L will cancel out, and I have 2I over x, but I'm gonna rewrite that. Let's say I'm gonna use R to write it. So this expression is true if I'm using R, if R is much less than the length of the wire. If this assumption is not true, then you will need to go back and use the expression we derived in the different video that includes no such assumption for the distance from the wire. Now, one thing I want to point out there are two ways with which you can make this assumption to be true. You can either move your observation location very close to the wire, or you can make your wire very, very long. Now, some problems will tell you that you have an infinitely long wire. Do you really have an infinitely long wire? Of course not. There is no such thing. What that statement means is that your observation locations, or where you want to find the magnetic field, is so close to the wire itself that this assumption is practically true. It is a valid assumption, and then you can go ahead and use this one, which is a much more simple expression than that.